In my previous lecture, I talked about reconstructing a function that we don't have based off of knowing its derivatives. So let's take a look at, kind of a fun real world situation. Okay, still maybe a little contrived, but let's have a function which predicts the height of an object. Could be any object you like. And, to begin with, I don't know what this function is going to look like. But I have an understanding of what acceleration this object should have, and I have an understanding of what velocity this object should have. These are some of the basic ideas in physics. So let's say that this object was launched straight up, and its velocity to begin with was 10 meters per second. And here we'll be using positive numbers to mean up and negative numbers to mean down. So that's going to tell me, at least for one instant in time, that the derivative of my function was 10 meters per second. So I'm going to use, let's say, h of t is going to be the height of the object after, let's say, t seconds after launch. This is telling me that h prime at 0 should be equal to positive 10. Now, this is a far cry from knowing the derivative of that function everywhere. All I know is that the derivative of this function was equal to 10 for some moment in time. However, this setup is telling me that I can approximate gravity in terms of constant acceleration. So near sea level, on this planet of ours, gravity imposes an acceleration of about 9.8 meters per second squared, right? So acceleration governs how much our velocity changes. The units for that are going to be in meters per second squared. And as long as we are, relatively close to the surface of the Earth, that acceleration shouldn't be changing by too much. Remember, we've got sort of an inverse square law that governs the acceleration due to gravity. And what's different here, different from the information about the velocity, is that this is going to be a constant. So this is a simplifying assumption that makes this equation easier to work with, that my acceleration, or my second derivative, is going to equal negative 9.8. And if you want units on here, that's negative 9.8 meters per second. This should be in, say, meters per second, and then this will be in meters. So using these theoretical ideas I had from yesterday, if my second derivative is a constant, what kind of function can have a constant as its derivative? Only a linear function can have a constant as its derivative. So my h prime of t has to follow a specific formula it has to be negative 9.8t plus some constant. And for right now, I don't know what this constant is, but I can find out. So how do I do this? There are infinitely many antiderivatives that velocity function could have been. Oh, right, I just need one extra piece of information in order to figure it out. Where is this extra piece of information? It's right here. So I have the y-intercept for this velocity function. H prime of 0 is supposed to be 10. And actually, I have exactly the formula for this. It's negative 9.8 times 0, t is equal to 0, for this equation, plus c. Well, I'll get rid of that 0. Anything times 0 is 0. My constant is 10. So this calculation is very quick, and it tells me that the formula for my velocity function is negative 9.8 times t plus 10. There it is. Okay, so what I just solved for is the velocity function. This is the derivative of the function I actually want. I wanted the height function or the position function. So what am I going to do next? I'm going to take another antiderivative. So if this is my first derivative of the function I care about, what kind of formula does the height function have to be? What kind of function can have a linear polynomial as its derivative? Only a quadratic function, only a quadratic polynomial. So this has got to be negative 9.8t squared plus 10t plus a constant. And I need to divide here. Let me just draw that in by hand. There we go.